Good morning, everyone. Good morning. Hope all is well. Hope everyone's doing all right. Hope everybody had a great weekend. Last class, we just did a review day. You guys asked whatever questions you had at the time. That closed out chapter 1 for us. So today we are looking to begin chapter 2. All right. All right, so don't copy that red box. The red box is notes for me. So we're looking at bases of functions. We're gonna go to another notes page that have this other stuff on. Just waiting for everybody to get in here. Once again, that red box is for me. In a few seconds, I'm gonna go to another page with notes. Oh yeah, not a problem, not a problem. Thanks for letting me know. All right, 2.1 basis of functions. And let's go to that page 154. All right, so let's start with the definition of a function. Not function, definition of a relation, I'm sorry. So a relation is any set of ordered pairs. So here we have the example 1, 2, 3, 4, 5, 6. So any set of ordered pairs is considered a relation. The domain is the set of all first components of the ordered pair. So in this case, 1, 3, and 5. And you arrange the set of all these second components of the ordered pairs. 2, 4, and 6. So next we just have a complete comparison between domain and range, like you already mentioned, first component versus second component. That means your domain will be your X variables and your range will be your Y variables. Domain's input, range output. Domain is independent variable, range is dependent variable. And then also that means your domain will be your horizontal axis while your range is your vertical axis. All right, done with the blue. All right, so definition of a function. A function is a relation or a set of ordered pairs. Is a relation in which the elements from the domain corresponds to exactly one element in the range. So once again, a function is a relation in which the elements from the domain corresponds to exactly one element in the range. So first exercise, we want to determine whether each relation is a function. So the first one is 1,626,3849. So we're going to create a mapping, and I'm going to erase this right here. So we created a mapping for our domain and range. Notice the first one, the circle, the domain, I have 1, 2, 3, 4, which came from our ordered pairs. And then in the range, we have 6, 8, and 9. Those are the only values in our range. All right. So we're going to create a mapping. In other words, 1 goes to what, 2 goes to what, 3 goes to what, 4 goes to what. Now, don't forget the definition of the function. Each element in the domain corresponds to exactly one element in the range. So if you can answer yes to that statement, does each element in your domain go to just one element in the range, then it is a function. So we have 1 goes to 6, and it only goes to 6. So that's yes. It only goes to one value in the range. 2 only goes to one value. It just so happens that, somebody trying to come in here. It just so happens that it's going to the same value as 1, but we're not looking at, is it going to multiple, are 2 values going to the same thing? We're asking ourselves, is the one value in our domain going to exactly one value in the range? And the answer is yes. And then same thing for 3. And then 4 goes to just 9. So that's yes as well. So if you can answer yes to all of those, then yes, it is a function. Okay, so your domain, your value in your domain has to go to exactly one element or one value in your range, then it is a function. All right, questions before we look at another example? Don't copy that purple, it's something else, but a good. Okay. All right, so this one, we have 61628394. Same question, is it a function? So once again, we're looking at our values in our domain and asking, is it going to just one element in the range? So we look at 6 is going to 1, and 6 is going to 2. So off the bat, we see that our answer is no, because we have this one value in our domain that's going to 2 values in the range. So that means it's not a function. So I have two general statements about functions that we can conclude based on what we just did. But any questions before I scroll up?
So, Mr. Tucker,
Mm-hmm.
so like you said, if there's one domain that goes with two of the ranges and it doesn't make it a function, can you have two domains go with a single range?
Yes, that was in that first one. That's what happened here. We have two values in our domain goes to that single range, and that was a function. Is that what you're talking about?
Yeah.
Mm-hmm. Yep. So that can be a function. And that's as long as, let's say 2, for example, as long as 2 doesn't go to another value, then there's all of this. As a matter of fact, 1, 2, 3, 4, all of them could have went to 6, and that's still considered a function, as long as that's the only value they go to. But it's just that when you have a value in your domain going to multiple values in your range, that's when you don't have a function.
Okay, thank you.
Mm-hmm. So if we look at the scenarios, the scenario that created a function and the scenario that stopped us from having a function, we can generally state that there can be a repeated value in the range, but no value can repeat in the domain. We had 6 that was repeated in the range, and that was a function. But when 6 was repeated in the domain, it was not a function. That goes back here. See how here's repeated in the domain, so it stopped it from being a function. Then here the range can go to more than one value, but the domain can only go to one value. All right, and by still copying, can I go to the next page? All right. So we're back here. We're looking at determine whether each is an equation that defines y as a function of x. So this time we have our function set up. Our equations, they give us an equation instead of just ordered pairs. And so our first equation is x squared plus y equal to 4. So we'll look at the steps on how to determine. All right, so first step, so we want to solve our equation for y. So that's what we did here. We had x squared plus y equal to 4. So to solve for y, we subtract x squared from both sides. All right. Next step, we want to evaluate to see if multiple y values can be produced by, and I probably should say by one x value. I'm gonna put that in there. So evaluate to see if multiple y values can be produced by one x value. So basically, you would just plug in values like +1 and -1, see if it's possible to get multiple values. And doing it like this, you probably say, well, I'm always going to get just one value. When I show you the next one, you'll see what I mean by that. But no matter what you do in this case, you see what I wrote in the blue, each x value will just produce one value, one y value. So we're okay. This is going to be a function for us. I'll try to give you guys a chance to write before I scroll all the way up. But in the next example, you'll see there is something defining in our problem initially that will dictate that we will get more than one value. So a simple problem like this, you wouldn't get more than one value, but it's something specific that will do that for you. Mhm. And so here it's just the work in the red, it's just the work of me plugging in the values, getting out that y. But this is a function because every time I plug in an x value, I will always just get one y value. Even if it's the same one, remember it's okay to have your y repeat. It's just that one cannot go to multiple y values. And like I said, in the next one, you'll see how that is a possibility. All right, scroll up. So for this next one, that defining factor or characteristic that I was mentioning is an even power on your y. Notice we have x squared plus y squared equal to 4. Last time we have x squared plus y equal to 4. This time we have x squared plus y squared equal to 4. So you want to look for that even power on your y. Because when you go ahead and solve, remember the first step was to solve for y. You will subtract x squared from both sides. Then you have y squared equal to 4 minus x squared. And then you'll take the square root of both sides to get y by itself. Now, don't forget, whenever you take the square root of both sides, you have to use the square root property. Square root property will produce plus or minus. And so that's how we're going to get that duplicate, not duplicate, but the multiple values for y. Scrolling up. So when I plug in 1 for x, I get plus or minus square root of 3. And so that means when I plug in 1, I get out a positive and negative square root of 3 or a positive and negative answer. So that 1 is going to 2 different values. So that stops it from being a function. X produced 2 y values. So this is not a function. But that only occurs when you have an even power on your y. All right. Scroll up. All right, so the vertical line test, if any vertical line crosses or touches a graph more than once, it is not considered a function. So if you have a function, you want to test to see if it is a function. If you have an equation or a graph, if you have a graph and you want to see if it represents a function, if you draw a vertical line through it and it touches it more than once, then it is not a function. So for the first one, if you have a circle, you draw a line through it, a vertical line through it, it touches it more than once, of course, so that means the answer is no. It is not a function. If you have just a straight line, no matter where you draw your vertical line, it will always cross it just once. So yes, that is a function. If you have a parabola, just a U shape, that U continues to get wider and wider, so it doesn't go straight up. So no matter where you draw that vertical line, it's only going to touch it once. So that means yes, it is a function. And the last one, whatever this shape is, even though when you draw vertical lines over here to the left, it only touches it once. When you get over here, it touches it 3 times. So that stops it from being a function. So once again, if you have a vertical line and you draw it through your graph and it touches it more than once, that graph is not considered a function. All right. Scroll up. You okay? All right. So next we're looking at function notation. Y equal to f of x. Mhm. So if you have y equal to 2x plus 1, you can interchange that y with f of x, and that's considered function notation. So it doesn't change the value of the equation. It doesn't change how you work with the equation. It's just that one is in function notation, one is not. If it says y, it is not in function notation. If it has f of x, it is now in function notation. From this point forward, they would expect you, no matter what class you go to or whatever, they will expect you to understand or remember that y and f of x are interchangeable. They mean the same thing. If you see f of x, then you know that represents y. If you see y, you know you can substitute in f of x for that. So there, that will be always the connection they expect you to hold on to. So once again, they don't change, that doesn't change the value of anything. It's just notation. One is in function notation and the other one isn't. So what that does for us though, even if this didn't say find, if all you saw was f parentheses 3, that's considered f of 3. If you want to know what that represented, that just means you would take 3 and then plug it in for x. Now you do have to have f of x defined already. You can't just say find f of 3 and then you don't have a function. So you have to have f of x already, and then if they ask you find f of 3, you will plug 3 in for x. So just another way mathematicians use symbols to give you a set of directions without actually writing that many words. So you plug it in and you get 7. So f of 3 equal to 7 is also the ordered pair 3, 7. X was 3, because we plug it in, you got out 7. Yep. questions on anything that we did. Over here, I wrote that would be G of T, you know, because you can use other letters other than F of X, F and X. That would be G of T. Over here would be S of R, you know, so if you're dealing with functions and you're writing in function notation and you use a letter parentheses, another letter, then you would just put an of in between those two letters. All right, questions. Let's scroll up. All right, so the next one, f of x is equal to x squared plus 3x plus 5. So once again, notice you have to have f of x first. Then they tell you to find f of 2 and then find f of x plus 3. So f of 2 just means plug in 2 into the function. 2 squared plus 3 times 2 plus 5. All right. Calculation, finish the calculation, you get 15. Do the same thing with x plus 3. It's x plus 3 squared plus 3 times x plus 3 plus 5. So you can expand, distribute, and then simplify as much as possible. So x plus 3 is x plus 3 times x plus 3. So you do the formula over here that's in the blue circle. That gives me x squared plus 6x plus 3. I mean plus 9, excuse me. And then distribute that 3. And that's 3x plus 9. And then plus 5 still in the back, in the back. Then you combine your like terms, 6x, 3x, give me 9x, 9, 9, and 5 will give you 23. Any questions? So we'll at least start 2.2. Not necessarily looking to finish, but at least get in there. Is everybody okay? Can I scroll up? All right, so we're looking at more on functions. So on an open interval, as x increases, y increases. So you're going from left to right. You always follow your graph from left to right. As you're going to the right, if you're going up, then it's considered increasing. And that's what I'm showing right here. If it's going up, it's increasing. If you're going from left to right, if it's going down, then that's decreasing. Everybody good? Can I scroll up? And then the third one is a constant. As x value increases, in other words, as we go from left to right, the y value stay the same. All right, can you scroll up? Everybody good? All right, so this first example under this, I want to state the intervals on which each is increasing, decreasing, or constant. So let me erase some of this stuff so we can walk through it. All right, so this first one, it's not really a definite, it's not really a name to the shape, but you're reading it from left to right. We're not following those arrows going down or anything. We're reading it from left to right. So from left to right, we're coming from negative infinity, and we're going up to this point right here. Notice I wrote here in the red that you always use your x values. Remember, we're reading as we go from left to right. So we're using our x values to set up our intervals. And we stop right here. Our first inflection point is right here at -2, x being equal to -2. So from negative infinity to -2, it's increasing because it's going up. Then from here to here, which is the next change in direction, is constant, it stays the same. So from -2 to 2, oh, I put it in the wrong spot. From -2 to 2 is constant. And then for the last one, once again, following from left to right, from 2. And notice, remember, we're going from left to right. So we're not going down as far as what we're writing our interval as. That's the direction we're going, but we're going to the right. So that's positive infinity. As we're going down, we're going to the right. So that's going to go from 2 to positive infinity as it goes down. So that's our decreasing. All right, so make sure we are okay with what we did there. All right, is everybody good on that one? So here, same type of deal. We follow from left to right. So this time we're going down. So that's coming from negative infinity to 0. Remember, we're looking at this point right here where x is. Then we're going up. So that's going to be increasing So it's going from 0 to 2. And we're going down again as it goes to the right. So we use our union sign. You guys will always be using the union sign. We have multiple intervals. And it's going from 2 to infinity. And we had no intervals that were constant. And those we use parentheses on all of our intervals, no brackets. All right, very good. Scroll up, very okay. All right, relative extrema. So it's just the maximum value relative to an open interval for our relative maximum. And then our relative minimum is the minimum value relative to an open interval. So in other words, the largest value in an interval, smallest value in an interval. All right. So just a generic diagram right there on the bottom, right under relative minimum. What do we mean by that? Because if you notice, this goes to positive infinity, this goes to negative infinity, this goes all the way up, goes all the way down. So there's no real legit maximum and minimum. So you can just have relative maximums or relative minimums, smallest values in the interval. You know, you have peaks and valleys when you have these waves. So those would be considered your relative max or your relative min, because once again, since it goes up to infinity, down to negative infinity, there's no real maximum or real minimum. Same thing over here, like with parabolas, your vertex would either be your relative max or your relative min. Well, in that case, though, with parabolas, it will actually be your minimum and maximum, but you can create intervals within that as well. But yeah. All right, so let's scroll up. And so they really didn't talk much about that. I think at the most they said use a calculator to find that. Let me see something real quick. Yeah, I think they just said use a graphing tool to find that. If you have any questions on that, let me know. You know, when you go into your homeworks. But I think that's all. They really didn't talk about, just because you're in calculus, you get into relative maximums and relative mins and stuff. But I think we're just introducing it here for the most part. That's why I didn't do anything else. But they just use a graphing tool to find it. So if you have trouble with that, always let me know. Let me see, it's 8:44. Yeah, we can do these real quick. Okay, definition of symmetry. We have three different ones. We have symmetry with respect to the y-axis, symmetry with respect to the x-axis, and symmetry with respect to the origin. So the first one, symmetry with respect to the y-axis. For every point on the graph, the point negative xy is also a point on the graph. So the way you would test for that is to substitute negative x for x in the equation. and see if it results in an equivalent equation. You know, what you had originally. So of course we'll do examples of it, but put each one of the standards first. Mhm. Symmetric with respect to the x-axis. For every point on the graph, the point x negative y is also on the graph. So in this case, we'll substitute negative y for y. And see if it results in an equivalent equation. And the last one, symmetric with respect to the origin. For every point on the graph, the point negative x, negative y is also on the graph. So in this case, you plug in negative x for x, negative y for y, and then see if it results in an equivalent equation. All right, can you scroll up? So let's go ahead and try this out for all three. Determine whether the graph of x equal to y squared minus 1 is symmetric to the y-axis, x-axis, or the origin. Doesn't matter which test you apply first. Just have to follow, the procedure for all three individually in order to determine symmetry. So our original equation, x equal to y squared minus 1. So plug in negative x, 4x. That's what I did right here. And then you would solve it. I would put it into the form that we have here. We have x equals. So I would solve it for x and then see what's to the right of x and see if it's the same thing that you have originally. So you have negative x equals the y squared minus 1. But I want to make a clean comparison and say x equals. So I multiply both sides by negative 1. And I have x equals to negative y squared plus 1. So you multiply negative 1 to both sides because once again, I want to go x equals. What is x equal to? And I notice I have negative y squared plus 1. So since this is not the original equation, the function is not symmetric with respect to the y-axis. So I would need this right here to be exactly what this is in order for it to be considered symmetric. All right. Any problems with that one before I scroll to the next one? All right, so the next one, symmetric with respect to the x-axis, or symmetric to the x-axis. This time we substitute negative y in for y and do our substitution and simplification. Plug negative y in, that'll be negative y squared minus 1. That negative is going to cancel out because negative squared is a positive. Negative y times negative y is a positive y squared. And since this function is the same as the original, it is symmetric with respect to the x-axis. All right. Got it for the last one. Symmetric with respect to the origin. So this time we're plugging in negative x for x, negative y for y, and see if we get the original equation once we simplify it as much as possible. So negative x and then negative y squared. So we already mentioned how the negative y squared will turn into positive y squared. Negative y times negative y will be positive y squared. Then once again, I want to get that negative off of x so I can make a clean comparison to what I had originally. So I multiply both sides by negative 1. X is equal to negative y squared plus 1. And once again, since this function is not the original, it's not symmetric with respect to the origin. Any questions? Any questions? What do I want to say? Even functions. Two functions. We can pause right here. This would be a good place to stop. We'll pick up with even functions, even and odd functions on next class. All right. So before we go any further, is everybody all right? Any questions before we close out? Everybody good? Everybody straight? All right. So if you guys are good, I'm good. Have a good day. Be safe. And I will see you on Wednesday.
Have a good day,
Have a
Mr.
good day.
Tucker.
Thanks. You guys do the same.
Thank you.
Thank you. Take care.
Thank you.